Okay, we study Y12, divergence, and Stokes theorems. According to Coulomb's law of electrostatic force, the electrostatic field due to a charge Q placed at the origin is like that. We know it follows the 1 over r square, that is inverse square law. The power 3 appears because the numerator is not a unit vector, but a vector x. So here x vector divided by its radius, that is just the magnitude of the x vector, is the unit radial vector. Electric field at a field point P with the position, this is a field point. We have to distinguish the field point and the source point. Here, the source is at the origin. Now, we have many charges, continuous charge. Actually, there is no continuous charge because there is an elementary electric charge is for the electron. So we cannot divide into many pieces, but for simplicity, we assume the integration is possible because it is very tiny already. So this mathematical expression does not mean E goes to 0, but the answer reaches the same limit. So we borrowed mathematical formula, but you must understand what it means. So charge, small charge dq is density at not the field point, but the source point multiplied by its volume, tiny volume. So this is the charge. So this is the charge. This is the charge for the point charge at the origin, and this is the charge. And we need to replace this ER with ER, capital R. That capital R is from the source. Source is at x prime, and field point P. This is Q, and field point. We measure the electric field at this point, and its vector is x. Okay? So we have the same r cubed, but this r is the magnitude of the vector relative displacement from the source to the field. And its ER hat is x minus x prime divided by its magnitude. Okay? So relative displacement vector divided by its magnitude q. The unit vector from the source to the field is like that. Okay. We need some algebra. Vector calculus. Divergence x. Divergence x derivative of x component, y derivative of y component, z derivative of z component. It's trivial. X, y, z components. 1 plus 1 plus 1 equals 3. Trivial. If x is not equal to 0, divergence of this one. Divergence of this one. Divergence of this one can be computed because it is a product of x times 1 over r cubed, y times 1 over r cubed, and z times 1 over r cubed. So product functions derivative, x derivative, y derivative, z derivative. So if I take these derivatives and keep it constant, then we have 1 over r cubed and divergence x. If I take the derivative of these, then what I get is a gradient scalar product. Why? X, Y, and Z. Okay, so what's that? This is X component of gradient. This one is X component, 1 over r cubed, y derivative, 1 over r cubed, and the z derivative, 1 over r cubed. Okay, so and scalar product with x. All right, gradient r. R is a square root x squared, y squared, z squared. If I take the derivative, it is x squared, y squared, z squared. And then chain rule. What's that? This is 2x. This is 2r. So 2x over 2r equals x over r. Just like that, x over r, y over r, z over r for x, y, z component. Oh, this is x vector divided by its magnitude. So unit radial vector, simple. Next, we compute this, 1 over r cubed gradient. 1 over r cubed gradient is chain rule. Because it is depending on radius only, first take the derivative with respect to r and take the gradient with gradient of r. So it's this chain rule. And gradient r, we know, unit vector. Gradient is a unit vector. And what's that? This is a minus 3 r to the 4th power. All right. Next, we need to consider this, sum everything. This one is this, and as shown in here, this one plus this, and divergence x, we know it is a 3. It is a 3. Divergence x is a 3 divided by r cubed, and x vector scalar product, gradient 1 over r cubed minus 3 r to the 4th power. Okay. Then what's that? ER hat dot x dot. This is ER hat dot RER hat. This is R, simply R. So R over R to the 4th power is 1 over R cubed. So 3 minus 3 is 0. Unfortunately, we are not able to this computation at x is exact 0. Even though its limiting value is still 0, I cannot substitute the 0 in the denominator, so it's quite important. We know that divergence goes to 0. However, it shall find the volume integrals including using divergence theorem. We investigate this problem more closely. Electric field is being radiated, and we choose a Gaussian surface that is a closed surface. Closed surface. So we attach the circle. electric field flux is integrated over this closed surface. And this is a scalar product, electric field, and infinitesimal surface vector. Surface vector means area multiplied by the unit normal vector along this direction. Okay, why don't we substitute the explicit electric field due to a charge Q at the origin? Then we know this is overall vector and this is a vector, one of our Q and area. This scalar product, what's the area? What's the area? We know the area later. We evaluate this, but just remember this divergence theorem. Surface integral, closed surface integral. This one should be expressed in terms of volume integral inside this closed surface. Volume integral of what? Volume integral of divergence. Replace with the volume. Okay? Divergence volume integral is the same as the surface integral. You need to copy the coefficients. So the answer is this. Because the charge is at the origin in this problem, at the origin at x equals 0. I can shrink this volume very small. Why don't we introduce an infinitesimal radius epsilon, a very tiny volume? This integral is 0 everywhere because why? Divergence of inverse square law is exactly 0 except for x equals 0. So that's the reason why I have removed all of the big volume except for the tiny sphere that contains the origin. So this integral is exactly 0 except for a tiny contribution at the origin surrounded by a sphere of radius epsilon that is approaching 0 but not equals to 0. Now, why don't we evaluate this integral returning to the divergence theorem over a surface with tiny radius epsilon. At tiny radius epsilon, this is radius q. This is radius r. And this is 4 pi r. What's that? 4 pi r squared. And epsilon, 4 pi r squared is the area of the sphere. And what's that? This radius r is epsilon. So epsilon cube exactly cancel. And this d omega represents the solid angle 4 pi. And this 4 pi cancels this 1 over 4 pi exactly. Finally, we have reached the Gauss law, charge divided by epsilon 0. By the way, charge divided by epsilon 0. Okay, what's that? The volume, tiny volume of a radius sphere of radius epsilon contains this charge. Then this charge Q must be the same as the one that can be integrated over a volume inside that the same sphere. What's that? This is density integral over volume must be the charge. Okay. The answer is, this function is a very strange function. This one, after integration, you need to find the charge Q in it. However, this value is obtained only if this volume contains this origin 0 at which the charge is placed. However, if you place this volume outside, this integral must be 0, whatever radius it may be, a very tiny one. So this density seems to be 0 everywhere. This density is 0. X is not equal to 0. This density goes to infinite, although the infinite y, charge q divided by volume, this 4 pi epsilon cube. This is volume, and you can take the limit epsilon goes to 0. This density is infinite, but mathematician would say, oh, we cannot compute anything, but physicists can compute this, although it looks uncomputable. If you integrate, the answer is trivial. This one is called Dirac delta function. And Dirac is a Nobel laureate, introduced the Dirac equation that is the relativistic version of the electrons Schrödinger equation, something like that. The relativistic equation for spin 1/2 particles that is called electron. And Dirac has created this function. And mathematicians didn't understand very well at the time, but now mathematicians like this Dirac delta function very much. Anyway, we have reached the point. This is nothing but the charge Q multiplied by the Dirac delta function. Dirac delta function is a function whose integral is volume integral is 1. And this is infinite or 0. Infinite at the origin only, and value is 0 everywhere. This is called the Dirac delta function, and we have found the normalization is like that because we know this formula. Why don't we divide both sides with the q over epsilon 0? Haha, that's the reason why 1 over 4 pi I copied, and this one is the Dirac delta function. Why? Integral is 1, and this integral vanishes everywhere if it does not include origin. Now we have reached the point. What we have done is the divergence of the electric field. What we have calculated is the divergence of the electric field. This divergence of the electric field. Divergence of the electric field, volume integral. That is, according to Gauss law, is a q over epsilon 0. So divergence of electric field is now identified to be density over epsilon 0. You now have this density is point charge q multiplied by the Dirac delta function. Okay. This is indeed Maxwell's equation for the electric field. In a similar manner, I can replace this electric field by magnetic field, and Gauss law for the magnetic field is exactly 0 because here it is a monopole, electrostatic monopole. So the answer to the magnetic field of the divergence should be the magnetic monopole, but nobody has found the magnetic monopole. Magnetic monopole does not exist in nature, as far as we know. So it is exactly zero. We have learned two important Maxwell's equation, two Maxwell's equations for the electric and magnetic field. Okay, these looks tedious, but the same calculation reproducing what I have told. And this is a similar one, but let me look at this. This is what we can obtain for divergence E is that subtracted by rho here. This integral is identical to this, and subtract this. Then integrand is like that. We shrink the volume very tiny at point X instead of origin. Choose the tiny radius epsilon and consider this a tiny sphere. Even though this volume is very tiny, its volume is not equal to zero. If epsilon is very tiny, this integrand becomes a constant measured at point X. So I can pull this one out because this integral is a trivial. This one multiplied by volume. Even though it is tiny, non-zero. So I can divide. Because it is a zero, we have reached the Maxwell's equation representing the Gauss law for electric field and Gauss law for the magnetic field. Magnetic field can be expressed like that. What's that? It is according to Theorems law. And you will find it is nothing but the core of a vector potential. We remember electrostatic potential. Electrostatic potential is 1/4 pi epsilon 0. Charge density at source volume integral distance between the field point and source point. They are very, very similar. The only difference is mu is in the numerator, epsilon 0 is in the denominator. This is a charge density. This is current density. What is the current density? Rho times V is the current density. So it is a very, very similar. At the time, by the time they constructed this kind of theory, they didn't know that these scalar and these vector has a close relationship. In relativity, Einstein showed that this is the zeroth time component and there is a spatial component for vector. We will learn later. Anyway, this magnetic field can always express in terms of a curve of the magnetic vector potential. Remember, electric field is expressed as a minus gradient of potential. Logic is very similar except that we have cross after the del operator. The reason is that magnetic field is always, V cross B, perpendicular to the magnetic field. The force is perpendicular to the magnetic field. So this curve has a close relationship with the Lorentz structure of the Lorentz force. Let us prove Ampere's law. This is a differential form of Ampere's law, but the integral form of the Ampere's law can be constructed first. What's that? There's a current. Magnetic field is rotating about a straight wire carrying a current I. Ampere's law is magnetic field integrated over a path, closed path, is mu 0 I, where I is the current, net current enclosed by the closed path. We make use of Stokes' theorem to prove this. This one is identical to the scalar product of the surface element and curve. That is called Stokes' theorem. We use this, and this is current I. We express this current I as current density multiplied by a scalar product with the surface element over this surface. Aha, we equate this. We equate this, then curve B minus mu 0 J dot this sigma equals 0, whatever surface it may be. We shrink this surface into very tiny surface, then integrand will become constant. We can factor this integrand, then the surface vector is a tiny pi r pi epsilon square area and hat vector. So in that case, this one is always 0, therefore this one must be 0 in the limit epsilon goes to 0. Therefore, we finally obtain the differential form of Ampere's law. And actually, this Ampere's law is not perfect. Maxwell has found that there is a missing component that is called the displacement current. There is not an actual current, but if you place a capacitor, current flows in, electric charge is being accumulated, and current flows out, electric charge is decreasing, so it is a negatively charged and positively charged. You will find the changing electric field is increasing as time goes by. The changing time-dependent electric field will generate the magnetic field that was guessed and discovered by Maxwell. So Maxwell is a genius who has found all the symmetric structure of the electromagnetism. Okay, that's it for today.